All right, problem number 4918. So in this problem, we're given the vector space, which is a direct sum of space U and space W. We're also given two linear operators. The first operator takes vectors from U and maps them into V. And vector in linear operator T2 takes vectors from W and maps them into V. It is given that these operators are linear. It is also given that we have operator T, which is the direct sum of T1 and T2, such that T takes vector V from the space V and decomposes that into the following structure: U plus T2 W, given that for any V, V can be represented as U plus W for any V from V, right? So this is equivalent of saying that T is a restriction of T1 is a restriction of T by U, and T2 is a restriction of T by W. We can even visualize that. That would be like subspace U and subspace V. They're kind of the subspaces of the subspace of V. And then there is V essentially, and then linear operator T1 and linear operator T2. And yeah, that's pretty much it. So the goal here is to prove that our T operator is actually linear. Well, that's a pretty simple problem, quite obvious. All we have to do is to prove two things: homogeneity and additivity, because homogeneity and additivity results in linearity. So for homogeneity, let's imagine we have the vector lambda v, which by definition can be decomposed into T1 lambda u plus T2 lambda w. Why? Because if for any v from the space V is u plus w, then lambda v is lambda u plus lambda w. And we know that lambda w belongs to u, upper u, and lambda w belongs to upper w, where lambda is some sort of scalar which belongs to the field. Given the fact that T1 and T2 are linear by definition, we can conclude that T1 lambda u equals lambda T1 u, and T2 lambda w equals lambda T2 w. Therefore, T lambda v equals lambda T1 u plus T2 w. Because of left distribution property, we can factor this scalar field value, and then we have lambda, which is by definition TV. So this is the exact homogeneity, since our T lambda v equals lambda TV. Homogeneity is proven. Now let's prove additivity. Suppose we have V1 plus V2. V1 can be represented as U1 plus W1. V2 can be represented as U2 plus W2. U1, U2 belongs to U, upper U, and W1, W2 belongs to upper W, which can be represented as T1, U1 plus U2 by definition, plus T2, W1 plus W2. And since they're linear, we can conclude that this is T1 U1 plus T2 U2 plus T2 V1 plus T2 V2. And now that's pretty simple. T1 comes with T2 V1 and T2 U2 comes with T2 W2, which gives us T1 U1 plus T2 W1 plus T2 W2 plus T2 W2, which equals to T V1 plus T V2. Therefore, our T V1 plus V2 equals T V1 plus T V2. This is additivity. Additivity is proven as well. And consequently, we can conclude that T is linear. In general, we can even show that the linear operator of sum of lambda I Vi equals the same as, let's say, the sum of T1 lambda I belongs to indexing set, plus another sum of T2 lambda I Wi, which is the same as the sum of lambda I T Ui plus Wi by definition, which is the sum of lambda I T Vi. I belongs to indexing set, and we know that Vj equals by definition to Uj plus Wj. So this is just in general. I mean, that's a pretty simple problem.